All right, so section 12.6 is about outliers. And, outliers are datums, data points, ordered pairs within two random variables where they're being related, looking for a correlation. So outliers are going to be data points that are kind of far and away from the overall pattern of like a linear pattern of like a line of regression. And typically, outliers are something that you want to look for at the very beginning before you progress and come to your conclusion with the quality of the line of regression that you've created. Because outliers can have significant effects on that line of regression. And in the end, I'm going to show you how much of an effect it can have. And by finding one and then removing it, and then seeing what the line of regression looks like afterwards. Um, and looking for outliers in two dimensions, in two random variables, is a very similar idea to looking for outliers when we only had one random variable. So when we had one random variable, we used like the interquartile range, and then we added, the interquartile range times 1.5 to third quartile. And then we took the first quartile and subtracted from it 1.5 times the interquartile range, and that gave us an upper boundary and a lower boundary. And any values that we had in our data set that were outside those boundaries, we could label as outliers. So we're going to do something very similar here. In two dimensions, there are other ways to have outliers. Okay, this is just one particular scenario that you can have outliers. Okay, that we're focusing on. So let's look at this first definition of error and residuals. So a line of regression either overestimates or underestimates the collected data. Okay, so what do I mean by that? So here we have this line of regression. And what you can see with this line of regression is that compare this line of regression to this first data point. So you'll see that compared to this first data point here, the line of regression is lower. This line of regression is lower than this data point. So the line of regression at this moment is underestimating the data. Now the next point, switch to another color. Okay, the next point, which is this one, it is below the line of regression. So the line of regression at this point is overestimating the data point. So here the line of regression is overestimating this data point. It's overestimating that data point. It's overestimating those two. And it appears to be, come on. It appears to be slightly underestimating that one and underestimating that one. And I think underestimating that one. Okay, so that's what I mean by a line of regression either overestimates or underestimates the collected data. Now, the amount of over or underestimation we call error. So you see the distance between the data point and the line of regression, this distance we call the error. And so we use the Greek letter epsilon, and I use this subscript 1 to show the error of the first data point is 34.73. So this distance, come on. So this distance from this point here to the data point, that distance is a distance of 34.73. And it's positive because we have to go in a positive direction above our line of regression. Now the next point, the line of regression overestimates it. So we have to go down from the line of regression to our data point. And that has an error of negative 19.09. So it's negative because we're having to go down in a negative direction to get to the actual data point from our line of regression. So the amount of over or underestimation is the error. So the error is the distance between the line of regression and our data point. Okay, so here's this other example here where the degree of underestimating is positive 15.768, and that's for the 7th data point there. Well, the 7th from left to right anyway. Another word for error is called a residual. Okay, so if you ever see like something where it says a residual graph, they mean a graph of errors. And I've already commented that you use the Greek letter to stand for error, and the subscript is the value. The subscript is the index of the data value that you're referring to. So for example, this third exam score versus final score of statistics students, we get this line of regression. And if we take our line of regression and we put that on a scatter plot, I've kind of labeled here what the errors are for a few of those. All right, now in the NumWorks calculator, it offers you what's called a residual plot. So it's an XY plot where the horizontal x-axis is the independent variable, the x values, but the y-axis is the error value or the residual value. Okay, now these screenshots are taken from the NumWorks calculator. So you'll notice here that this point on the left had an error of 34.73. So that had an x value of 65, and it had an error or residual of 34.73. Well, look at this graph here on the left. If we look at this point at 65, and we go up in the y direction, here's 20, here's 40. This value right here is 34.73. So this is a graph of x values here on this horizontal axis, and the vertical axis is the amount of error at that x value. So if you look at the next data point up above, that is an x value of 66. And at an x value of 66, we had an error of negative 19. So you look here at 66, and you look here at negative 20, right? Negative 19 is almost negative 20. And you can see we have this red dot, which represents the error for this particular data point of negative 19. So you have this range of x values here, and you have the error for each one of those data points. And notice that right now this data point here is being selected. And at that data point, it tells you exactly what the error is, 34.732733942. That's the same as this number up above. And if I use like the right and left arrow buttons, I can switch from selecting that point to maybe this point down here, which is what I've done here in this screen. And you can see its residual is negative 19.09. Now, one thing to keep your eye on is this residual standard deviation number. this residual standard deviation number. In a previous section, the Texas Instruments calculators calculated a value. Sometimes it would just be the letter S. I think I programmed one where it said S error. Okay, that was this value of 16.41. Let me scroll down. So, how do you make this residual plot, like on the NumWorks calculator, for example? Okay, I've got these instructions here, but let me show you how to do that. So let's look at the NumWorks calculator first. So first you want to go to the regression app, click OK, put in your data values, go to graph, and at first you won't see this line of regression. So let me go up, and let me just go and take that off. So this is what you would have. So now you want to go ahead and do a regression, make it linear, then go back into the regression option again, and you'll notice it gives you more information than what you had before. Now that you've chosen a linear regression model, okay, it's giving you the line of regression equation here. It's giving you the correlation coefficient here. Here's the coefficient of determination, which is just the square of that. But this is where you can do a residual plot. So if we click OK, now we have a residual plot. Now, unfortunately, I don't really see any way that we can maybe change these axes, but here you go. So right now, this first data point is selected, so it's telling me it has a residual or an error of 34.73, and I can scroll to all these different data points, and it gives me the error for each one. Another way to look at it is maybe look at it as though this horizontal line is actually your line of regression if it was flattened out horizontally. And this is the distance from the line of regression to that data point. The distance from the line of regression to that data point. Line of regression to that data point, and so on. Okay. On the Texas Instruments calculator, we can't generate a graph like this. At least as far as I know, there isn't a function to do that. But instead, we could get these residual values. So for that, we want to go into the list editor. So let's do that. So first, make sure that you've got your X and your Y values. Okay, then come up here to list 3, or the list next to your Y values like this. And what we want to do is we want to look at this list option above stat. So we need to hit the second blue button here with the stat button. And you see right here, it says resid. That stands for residuals. So what we're going to do is we're programming list 3 to be composed of residuals. Right? So I have list 3 selected. I hit second in stat, and I chose resid for residuals. So list 3 is going to be equal to the residuals. So if I hit enter, so notice it gives me 34.733. Give me a second. That 34.733 is the residual of this first point right here. Okay, so this first point, that's the residual, and that's equal to this point's residual. So here it gives all the values. It doesn't give you a graph. Okay. Now there's a residual standard deviation. And the residual standard deviation um, has a lot of different, um, gosh, I want to say labels. Let's put labels. So the standard deviation of the residuals is shown as an S on the Texas Instruments calculator functions, LinReg T test and LinReg T interval. So LinReg T interval is what we used to answer question 4 earlier in the chapter. Um, in the program that I wrote for LinReg T interval, let me show you. Here we go. Might take a little bit. Okay, we'll come back to that. On the NumWorks calculator, the standard deviation of the residuals is shown with an SR, and it's in the Stats tab under the regression app. So if we go back here and we go to the Stats tab, so we go up. Let's see here. I can't go up or down. Okay, so I think if we hit this back key, there we go. Now we can go up. We'll go to, let's go back again. All right, now we can go up, go to the Stats tab, and look along this column here. There should be one that says SR. Okay, not sample standard deviation, that's S. There we go. The residual standard deviation SR, 16.412. Okay. All right, let's go back here. So in the LinReg T interval function that I wrote, I put it S error. So the standard deviation of the error is 16.412. Okay. We need this value in order to look for outliers. Okay. And on this calculator, let me just go to that really fast. This one doesn't take long at all. There we go. So this value of S is 16.412. Okay, so this value of the standard deviation of error is what we need to find outliers. This is the formula that's being used to calculate it, but we won't go into that because your calculator does it for you. Here I'm just kind of showing you where you find it. So yeah, let's keep going. So here, LinReg t-test, but LinReg t-interval, this is the function that we've already been using, and this is that value there that I just showed you. Okay, so let's go back to thinking about outliers in one random variable. So we're going back to chapter 2 for a minute because I want to kind of show you the concept of what we're doing. So back in chapter 2, when we looked for outliers in one random variable, we'd have a data set like this. We would do a 5-number summary, which would give us a first quartile and a third quartile. And from the first and the third quartile, we would calculate an interquartile range. And if we took this interquartile range and multiplied it by 1.5 and added it to the third quartile, that gave us an upper outlier boundary. And then if we took this interquartile range, multiply it times 1.5, and we subtract it from the first quartile, that gave us our lower outlier boundary. So with these boundaries in place, if any of our datums were outside either boundary, we would consider those to be outliers. So in this example, you can see here we've got a bunch of numbers that are pretty close together, and then 12 looks like it's far and away from the rest. 12 ends up being outside this upper outlier boundary, which gets calculated to be 8.25. So 12 is beyond that. So 12 is considered an outlier. And, at this point, we would remove the outlier, and we have kind of like a new data set with the outlier 12 removed. And that ends up changing the rest of our calculations afterwards. So very similarly, we're going to have our data. And from our data, we're going to be calculating an upper outlier boundary and a lower outlier boundary, and then looking for outliers. Okay, but it's going to be in 2 dimensions and not in 1 dimension. All right, let's stop here in advance of the video to come. Let me know if you have any questions.